All right, let's get right into it. Today, we're digging into a problem that every single engineer has to deal with, one that costs a fortune every year. Why do welds always seem to be the first place corrosion takes hold? We're going to break down exactly what's happening at the microscopic level.
I mean, it's a super frustrating thing to see in the field, right? You've done everything by the book. You've got the right materials, a solid welding procedure, and yet, time and time again, that first little spot of rust pops up right on the weld seam. Well, I'm here to tell you that's not just bad luck. It's actually a predictable result of the physics and chemistry that happens during the welding process itself.
So here's the absolute key to understanding this. A weld isn't just a simple bond holding two pieces of metal together. No, the very act of welding actually transforms that joint into a tiny, self-contained electrochemical cell. It's like you've created an accidental battery that's literally designed to destroy itself.
Now this is where it all comes together. Just look at the different zones we have here. You've got the weld metal itself in the center. Then you have the base metal on the sides, which hasn't been changed. But that area in between, that's the heat-affected zone, or HIZ. And that's where this whole story of corrosion really kicks off. Okay, so to really get what's going on, we have to talk about a fundamental principle, galvanic corrosion. You probably remember it. It's the exact same thing that makes a regular battery work. You just need three things: two different metals, an electrical connection between them, and some kind of electrolyte. And as you're about to see, the welding process creates all three of those conditions in one tiny spot. So, because of all the intense heat and crazy changes happening during welding, the weld metal and that heat-affected zone become electrochemically different from the original steel. They actually become anodic. And what does that mean? It means they're just itching to give up electrons, which is, the very definition of corroding. Meanwhile, the cooler, stable base metal acts as the cathode, pulling in those electrons and staying nice and protected, all at the expense of your weld. And that difference in potential, well, it creates a current. You literally get electrons flowing from that anodic weld area over to the cathodic base metal. This flow, this is the engine that drives the whole corrosion process. But, and this is a big but, that engine can only run if there's a path for the current, a path that's provided by an electrolyte, which can be something as simple as a thin film of moisture. Okay, so we've established that the weld acts like a battery. But the real question is, why? What is it about welding that sets up this perfect storm? Well, it really boils down to four key drivers that we need to understand. Let's get into them.
Here they are, the four culprits. You've got microstructural change, residual stress, the surface geometry of the weld itself, and finally, environmental exposure. Each one of these plays a really distinct and absolutely critical role in setting that weld up for failure.
So, first up, microstructural change. Think about the intense heat from welding, followed by rapid cooling. It completely rearranges the metal's grain structure in that heat-affected zone. It's not the same uniform material as the parent metal anymore. This new, messy microstructure creates a patchwork of tiny anodic and cathodic sites right next to each other, basically laying the groundwork for corrosion to start.
Number two is residual stress. As that weld cools down, it doesn't cool evenly. This process locks in a huge amount of mechanical stress, especially tensile stress, right at the toe of the weld. Now, you should think of this stress as stored energy. An area with high stored energy is way more chemically reactive, which makes it much more likely to become an anode and just start corroding away. And third, we have something super simple, the physical shape of the weld. I mean, even the most beautiful weld bead isn't perfectly smooth, right? It's got little peaks and valleys, tiny nooks and crannies. And these little imperfections are absolutely perfect for trapping and holding on to moisture, our electrolyte, and keeping it pressed right up against the most stressed, most chemically active parts of the joint. And last but not least, we have the trigger. The first three drivers basically build the battery and get all the wiring in place, but nothing happens yet. It's environmental exposure, humidity, rain, condensation, that provides the electrolyte that completes the circuit. The second that moisture shows up, boom, the battery gets switched on and the corrosion process begins. So here's the thing. These drivers don't act alone. They all combine and interact with each other, creating what is truly a perfect storm for failure, right there at the weld. It's a spot that is uniquely and systematically engineered to corrode. And looking at this diagram again, you can see how it all comes together. The microstructural changes and the locked-in stress, they create the anode and the cathode. The rough surface geometry traps the moisture. And then environmental exposure is what delivers that moisture in the first place, flicking the switch and turning the whole system on. It's really a conspiracy between physics and chemistry, all working against your structure. Honestly,
I think the best way to think about this is that when you make a weld, you're not just joining two pieces of metal. You are literally assembling a pre-packaged corrosion kit. It comes complete with the anode, the cathode, and all the wiring. All it needs is for you to just add water and it's ready to go.
Which of course brings us to the most important question. What do you do about it? Now that you understand the why, the 4 drivers behind the failure, how does that change your approach? Is your first line of defense trying to control the microstructure with post-weld heat treatment, or maybe managing that residual stress? What about improving the weld geometry to avoid those moisture traps? Or is the most practical defense just a really robust coating system to deny the battery the electrolyte it needs to even turn on? That's something to really think about on your next project.